Let us take a look at the theoretical basis on which heat is used to do work in a piston engine. This is also known as the Otto cycle. Let us start with a piston containing gas. We can describe the gas inside the piston using the physical properties of temperature, pressure, and volume. So this gas has a particular temperature, which we'll call temperature cold, pressure, and volume. Now we can compress this gas, and therefore if we compress the gas, the volume will reduce, the pressure will increase, and the temperature could change or could stay the same, depending on whether we allow it to exchange thermal energy with the surroundings. Let's say that the piston now is in this position. Let's call it position 1. And position 1, at a particular temperature, has a specific volume and pressure, which we can actually plot on a pressure-volume graph. Now, what happens when we compress the gas? Compressing the piston, we see that the volume of the gas has reduced, and so this is shown in the graph here. The volume has reduced, and the pressure has, of course, increased to a new value. This requires work to be done. The amount of work done can be found by the area under the graph between V1 and V2. If this compression is done fast enough, there will be no time to exchange thermal energy with the surroundings, and therefore the temperature could remain the same. Since the temperature remains the same, we can call this an isothermal process. So in summary, in going from the piston's position 1, which was a position of a high volume and a low pressure, to position 2, which is a lower volume and a higher pressure, then we need to do work, and it's also an isothermal process. Now, let's see what happens in this case if this volume of gas was now ignited, so that fuel was burned and the temperature had actually risen. Since this ignition or burning will take place instantly, there will be no time for the volume to change, and so it's an isovolumetric change where the pressure goes up significantly higher in a very, very short period of time. So between 2 and 3, the fuel is burning, it's ignited, and it's an isovolumetric process that helps it reach a higher pressure and temperature. This high pressure and temperature is going to want to push the piston back out, and as the piston reaches position 4, or back to the original position 1, work is done by the gas on the piston. And so the work done can be found by the area under 3 and 4, which is of course larger than the area under the graph under 1 and 2. So the difference in area between 1, 2, 3, 4, this area enclosed in here, is actually the net work that is done. So between positions 3 and 4, work is done by the gas, and this process is also isothermal, but at a higher temperature than between 1 and 2. So 1 and 2 are at a colder temperature as compared to 3 and 4. As this process takes place quite fast, we also know it as an adiabatic process where no thermal energy exchanges are taking place. So not only is between 1 and 2 an isothermal process, but it's also adiabatic. Now, in order to repeat the process, we must go from 4 back to 1 so that we can repeat the whole process. And to go from 4 back to 1, the only difference is that the pressure is higher, the volume is the same. So at the same volume, we just have to release some gas, exhaust some gas, and therefore also some thermal energy. In exhausting this thermal energy, the pressure is relieved back to 1, and then the whole process is repeated to extract energy. And this is how a 4-stroke engine works. The first stroke is a compression stroke. The second stroke is when the fuel is burned. The third stroke is the energy provision stroke. and the fourth stroke is to restore it to the beginning situation so that the process can be repeated. So in summary, position 1, where the gas is cold, is then compressed to a small volume and high pressure. We then ignite the gas inside to increase the pressure dramatically and the temperature, which is then, this high pressure and temperature is used to do work on the piston. And at 4, we simply exhaust the gas to relieve the pressure back to 1 so that the process can be repeated. The area here represents the actual work done by the whole cycle. The shaded area represents the work done in going from 3 to 4 across this volume change and pressure change. However, there's also work done in going from 1 to 2, and so it is the difference in the work done between 3 and 4 and 1 and 2 that is actually the net work given. Because between 1 and 2, we are inputting energy into the gas. And between 3 and 4, the gas is now returning energy. So this yellow area here, between 1, 2, 3, 4, and back to 1, is the energy that is given out as work.